In the last session, we have seen that a machine or an engine consisting of a single slider crank mechanism produces unbalanced forces in a manner, a part of which can be balanced by placing a balancing mass as a counterweight to the crank, and the reciprocating mass produces an unbalanced oscillating force along the system center line, and it can be expressed in terms of an infinite series of harmonic quantities. As we know, this theta is nothing but omega t. If we take theta equal to 0 at t is equal to 0, then these are nothing but harmonic functions of time of continuously increasing frequency, and this is also an approximate situation, because we have replaced the actual connecting rod by two concentrated masses, one at the crank pin, other at the slider pin, which is not an exact replacement, but it does not introduce much error. So, even then this situation is like that, there is a primary component, the second harmonic, fourth harmonic, and so on, that we have seen. But it has been also pointed out in the past that it will be enough in most cases if we consider only up to the second harmonic. Thus, until and unless mentioned, now onwards we will keep our unbalanced forces under consideration only up to the second harmonic, or which we call the secondary. Now, we have seen that the primary component of the unbalanced force is something which can be produced by the centrifugal force generated by placing the reciprocating mass at the crank pin, and the centrifugal force which will be generated with its component along the engine or the system center line, that is nothing but the primary. But in that, remember that if we really place a mass here, it will also produce the other component. Thus, if we keep that in mind, that the force, real force is only along this, then the primary can be represented by placing this reciprocating mass here. Similarly, the secondary force can be considered as mentioned earlier as a component along this center line of the centrifugal force produced by placing a mass which is lambda by 4 m reciprocating at the tip of a hypothetical crank of same radius r, but rotating at double the speed of the primary crank. And we have seen that then component along this will be same as what the real system is, or rather the equivalent system with apportioned connecting rod mass, what that produces. Now, to neutralize these forces, it requires an active system by which we can again produce some balancing forces matching exactly the magnitude and being opposite in direction, and that we have also seen. However, the situation is much simpler, or rather very convenient in many cases where a system or an engine consists of more than one slider crank. Common examples are the engines. Generally, we find that engines of some considerable power are always multi-cylinder. So, in such cases, if we design the machine or the engine in such a manner that the unbalanced forces of individual cylinders or individual slider crank mechanisms, they neutralize each other, then it will be a very nice and convenient situation that the whole engine as a whole will be free from unbalanced forces. And now, what we start discussing is precisely that we consider how to take care of the balancing forces or unbalanced forces in case of multi-cylinder systems or multi-cylinder engines by suitable design. So, there are many ways where these multiple slider crank systems or multiple cylinders in an engine can be placed. One most common example or situation is inline engine. Now, in all such cases of multiple cylinders or multiple slider cranks, we have to keep in mind that each unit is identical to another one. What I mean to say, that the slider crank mechanisms for each and every component of that engine, they will be all identical. In inline engine, the configuration is something like this. So, in inline configuration, the center lines of each and every slider crank mechanism or the slider crank engine mechanism, the center lines are parallel. Next, the gap between each is something fixed, say A, it is uniform, and as already mentioned that each of these units are also identical in their dimensions and masses. Say let the connecting rod or crank radius for each will be R, connecting rod length be L. Then all these cylinders, they are driving their individual cranks, and all these cranks are actually driving a common crankshaft, which is actually running or driving the load, whatever it may be. So, this is an isometric view. So, to make our life easier, generally we will replace an isometric view by an engineering drawing like this. So, an N cylinder inline engine will look like this. Now, this being the cylinder number 1, cylinder number 2, cylinder number 3 and so on. Another condition you have to keep in mind, that when this system is running, then at one instant only one cylinder gets fired, in case of engines of course. So, therefore, we have to also keep in mind that each firing of individual cylinders, they are also uniformly distributed over time. That means, the whole cycle of the engine, when it completes, during that one complete cycle, which will depend on the number of strokes or the particular cycle the engine is following. It can be either 2-stroke engine or 4-stroke engine. So, in case of 2-stroke engine, the cycle or total period is given by 2 pi, that means one rotation, that is for 2-stroke cycle, that we know from IC engines. In case of 4-stroke cycle, the rotation of the crankshaft will be 4 pi or 2 rotations. So, if we have to distribute the firing uniformly over this whole period of the crank rotation, either 2 pi or 4 pi. So, therefore, the angle of rotation of the crankshaft between consecutive firing will be either 2 pi by n or 4 pi by n. This is angle So, thus we know that the crank has to be so designed or so arranged that the firing takes place at a uniform distribution or at uniform interval. So, if we take the side view, the crank may look like this. We can have a crank diagram which we call as for cylinder number 1, cylinder number 2 crank, cylinder number 3 crank, and so on. Say this is cylinder number n crank. And we have to also indicate always in a crank diagram the direction of rotation. We know, say, direction of rotation is this, and therefore, we can also see from this crank diagram we can also find out the firing order. Firing order in this case will be with this, the way we have kept is 1, next firing is for, because when this rotates by this angle which is say 2 or 4 pi divided by theta, depending on the number of cycles. So, this angle can be 4 pi by theta or 2 pi by theta. So, the firing order will be then first 1, then it rotates by this angle, then this comes to the top position and firing position, then 2, next 3 comes and that gets fired, and so on. So, now you will see, as we will just now find out, that this firing order is very important, because according to that only the crank locations will be arranged, and by the same engine with a different firing order and different crank settings can behave differently from the point of view of balancing of its forces and moments. Now, in case of single slider crank system or single cylinder system, there was only a matter of force, but now what we will have? We will also have a moment, because force is acting at different lines, and therefore, if this is the engine center line, this is the engine center line, not cylinder center line. These are the individual cylinder center lines, but midpoint of this engine is cylinder center line, and we can find out the moment of all these forces about this cylinder center line. So, now onwards we will have both unbalanced forces and unbalanced moment. As we have seen in case of rotary balancing also, that a system may be balanced from the point of view of total force, but if there are two equal and opposite forces passing or acting along two different lines of action, then they produce a couple, and that can produce unbalanced forces on the supporting bearings. Same thing here, because we have seen that the unbalanced primary force of each one can be represented by placing a mass or the cylinder mass here, and assuming that only the component along the cylinder center line that is only existing, rest is not existing. So, somehow we are now converting our reciprocating balancing problem into a rotary balancing problem. What we will now do to investigate the condition of balancing of this, we will place the masses here at the crank pins and see what state of balancing it produces. If we find that those masses M reciprocating, if we put at the crank pins, they balance among themselves, then obviously there any component will also get balanced. That means the real unbalanced force also will be balanced. If the moments produced by these hypothetical masses at the crank pins, the moment also produced is 0, then the component of the moment which will be actually there will be also 0. That means the system will be really balanced. So, what we will do, I will explain the whole situation, how to analyze multi-cylinder inline engine with the help of certain examples. So, first example, let us take a 4-cylinder engine which is working on 2-stroke cycle. This is the engine cylinder line, and obviously then this will be A by 2. Next we take the crank diagram, primary crank. First we will investigate only the primary forces and moments. So, let us keep the primary crank as 1. Now, if it is 2-stroke cycle, then the firing between consecutive, the angle between the 2 consecutive firing cranks will be 2 pi by 4, that is theta will be equal to, so pi by 2, and let the firing order in this case be 1, 2, 3, 4. So, this will be firing of crank 1, next firing will take place for crank 2, next after another 90 degrees 3, and next another, and of course, the primary crank is rotating in this direction. Now, one should never forget to indicate the direction of rotation, otherwise this firing order has got no meaning. Now, let us see what happens if we consider that the reciprocating mass of each cylinder and the apportioned mass of the connecting rod at the cylinder, they are placed here at the tip of the cranks. So, when it is rotating they are producing centrifugal forces, and let us see what is this primary force diagram. This primary force produced by the cylinder number 1 will be this, and this is nothing but m reciprocating omega square r. The primary force produced by the second cylinder, which will be nothing but the centrifugal force of this, only of course, we should remember it is only the component of those forces in this, but what we are initially doing is we are considering only the centrifugal forces produced by these hypothetical masses placed here. Now, if those centrifugal forces they themselves are balanced, then obviously their components along any direction will be also balanced. So, for cylinder number 2, the unbalanced force produced is this of same magnitude at 90 degrees. The centrifugal force produced by the third cylinder with that mass here will be this, and for by the fourth cylinder will be this, and so therefore, we call it primary force diagram. As we have seen in rotary balancing cases, that here therefore, what it means, if there are M reciprocating placed at the crank pins, they produce 0 total resultant force in the whole engine, because the force vectors they form a closed polygon. So, therefore, primary forces are balanced. It means that the primary component of the forces produced by the 4 cylinders, they neutralize each other. So, there will be no unbalanced effect on the bearings due to the primary forces. Next, let us see primary moment. Primary moment we always measure about the engine center line, about this point. Now, again remember that this what we have seen, we have drawn it from a viewing this in this direction. So, moment diagram also we can do, and we have seen previously that there are 2 ways of handling. Suppose if there is a force like this, so it will produce a moment which will be going inside the board, and when seen from this side it will be towards right. If all the forces are on one side of the point about which we are taking the moment, then we can do, we will get the same geometric figure of the moment components or moments. If we rotate the whole diagram by 90 degrees, we have seen that. Now, without going into such complicated cases, let us directly plot the primary moment diagram, looking from this side, that what these centrifugal forces will produce about this. Now, the centrifugal force magnitudes are same, it is m reciprocating omega square r for each case. Now, if this force is acting in this direction here, what will be the moment? When you see from this side, the moment will be like this. So, it will be going in this direction, and the moment is m reciprocating omega square r into 1.5 a. The distance from this to this is a plus half a, that is 1.5 a. Next is cylinder number 2. Here the when you see from this, it has come like this. So, force will be like this, as you can see. This is the first cylinder's force, second cylinder force in this direction like this. So, this will produce a moment in the upward direction. So, rather I think we should change this. In the upward direction, the magnitude of the force is same, m reciprocating omega square r, but the distance is only 0.5 a. So, it will be okay. Next comes, this is the cylinder number 1, cylinder number 2, cylinder number 3. Now, cylinder number 3 is here, the force is coming in the downward direction. That means, this force will produce another moment in this direction, and its magnitude will be again same as this, m reciprocating omega square r into 0.5 a, and this cylinder the force is in this direction, and obviously it will produce in the upward direction. Its magnitude will be again same as this 1.5 a m reciprocating omega square r. So, the resultant moment you can see it does not form a closed polygon. So, this is the unbalanced moment, that is a vector quantity, and the whole diagram is rotating. Of course, you have to see that this whole thing is rotating with the same speed omega as the crank. Just like a rigid body attached to the crank itself, the whole thing rotates, and the resultant being this at certain angles. But remember, the actual moment is not this one. Actual moment will be the moment due to the components of these forces. Now, since all the forces are in vertical direction in reality, so the real moment will be always in the horizontal direction. So, the component along this is the real moment, actual moment. So, when this is at this position, suppose this is in this position making a 90 degree with this direction, then moment is actually instantaneously it is 0. When moment is aligned with this vector, then the total moment is exactly its magnitude is same as m reciprocating the maximum value. So, the magnitude of primary or primary moment unbalanced and since it is unbalanced, it will fluctuate. Maximum magnitude is generally indicated by the maximum value. And that is equal to this, which you can easily find out. This is 1.5, 0.5, so 0.2. So, it is 2 root 2 a m reciprocating omega square r. This is the maximum magnitude of the primary moment. Now, this is the primary. Now, when we have to investigate the secondary unbalanced forces, then first we have to draw the secondary crank diagram. Now, we have seen that in any reciprocating engine or reciprocating slider crank mechanism, what is meant by secondary crank means it rotates at a speed twice that of the primary crank, which is nothing but the actual crank also, and at an instant it has rotated through double the angle. That means, if this is the primary crank, then the secondary crank will be this. Rotating with a speed omega. The secondary crank rotates at a speed 2 omega, and at any instant it makes angle 2 theta. So, if we have to draw, and we have seen that secondary forces can be also considered to be produced by the centrifugal force component and the centrifugal force is produced by placing a mass lambda by 8 lambda by 4 m reciprocating at the secondary crank. Now, so the angle what the secondary crank makes is twice the angle made by the corresponding primary crank. So, for cylinder number 1, what is the angle? If this is the center line direction, as you can see, angle made by the primary crank with the cylinder center line is 0, theta is 0. So, secondary crank will be also 2 into 0 is 0. Now, the angle made by crank 2 with this and in the direction of rotation as always you do. So, in the direction of rotation, angle made by crank 2 with the cylinder center line is how much? Is 3 by 2 pi or 270 degrees, that means 3 pi by 2. So, double of that will be 3 pi. So, therefore, it will be 1 pi, 2 pi, 3 pi. So, secondary crank will be here. They are all rotating at a speed 2 omega. Third crank is making in the direction of rotation from the cylinder center line how much? 90 degrees, 180 degrees. So, double of that means 2 pi. So, third secondary crank will be here, and for cylinder number 4 in the direction of rotation how much angle it makes with the cylinder center line is 90 degrees. So, double of that is nothing but 180 degrees. So, this is the secondary crank diagram for the same engine. So, now to investigate the secondary forces and secondary moments, we proceed in the same way. That first let us consider that we have placed a mass which is lambda m reciprocating by 4 at the tip of each secondary crank, and then the centrifugal forces produced, we consider their component along this cylinder center line. But before doing that, if we find that those centrifugal forces are balanced among themselves, then obviously their components are also balanced or 0. So, secondary force diagram will be, in this case, the first cylinder will produce a force lambda by 4 m reciprocating 2 omega square r in this direction. The second one will produce in the opposite direction the same magnitude. The third one will produce in the other direction the same magnitude, and the fourth one will produce, and the whole thing we have to keep in mind, we should show it. Now, here you can see that secondary force diagram is also a closed polygon, because you have come back to the same point where you started. And from this we find secondary forces balanced. Now, let us consider the secondary moment again in the same way, that the force which is produced in this direction there, it will produce a moment in the right hand direction like this, and that magnitude will be lambda by 4 m reciprocating 2 omega square r into 1.5 a. Then second cylinder produces, this is the first, this is the second, third, fourth. Second produces a force in this direction. So, therefore, it will produce a moment in this direction. Its magnitude is lambda by 4 m reciprocating 2 omega square r into 0.5 a. Then third one, now we have come to this side of this point, and here third one is again up one will again produce a force in this direction of the same magnitude, m reciprocating lambda by 4 2 omega square r into 0.5 a. And then the fourth one, which is force is in the upward direction here, and obviously here it is down. The downward force should go in the other direction. I am sorry. This is producing a moment in this direction, this is producing a moment in this direction. Now, this is in the upward direction. So, that is also producing a moment in this direction. I think I was right. Now, this one, fourth one is producing a force in this direction, that means it should go in the other direction. So, we started here, this is the first, the moment produced by the secondary forces of the first one cylinder, this is the moment produced by the secondary force of the second, this is the moment produced by the secondary force of the third, and this is the moment produced by the secondary force of the fourth one. So, this is the resultant magnitude of the leftover. How much is that? This is this plus obviously this will be 0.5. So, therefore, it will be lambda by 2 m reciprocating 2 omega square r a, and the whole thing is rotating as before. So, we find here secondary moments are also unbalanced. And how much is the maximum possible value, or what we call magnitude, is this. And at any instant, what is the value of the magnitude? It is, since the forces are all in vertical direction. So, their actual moment vectors will be always in horizontal. So, this component is the real instant. Since it is rotating, at this particular instant we get the full value, but at some other instant it will be inclined and we have to take only the component. But magnitude is given by the maximum value as it was done here. So, we find in a 4-cylinder inline engine operating on 2-stroke cycle, the primary forces are balanced, secondary forces are balanced, but both primary and secondary moment are unbalanced. Next, what we will do, we will go to a more realistic case when we take up a 4-cylinder inline engine operating on 4-stroke cycle. Here the angle between consecutive firing cranks is 4 pi by 4, that is equal to pi. So, in case of a 4-cylinder 4-stroke cycle engine, the angle between the consecutive firing cranks will be 4 pi by 4, that is equal to pi, and say this is the system. Now, so the primary crank diagram will look like this. Suppose we start with firing of 1, and if the firing order we keep as 1, 2, 3, 4, then first number 1 which is here, then next 2 comes up after 180 degree rotation of the crankshaft, then number 2 gets fired, Then number 3 comes up after a total of 2 pi, that means after 2 it will be again another pi. When 3 comes up, then that fires, and then finally another 180 degree rotation and crank 4, the cylinder number 4 fires. So, this will be the isometric view of the crankshaft, common crankshaft. So, in this case again we will now quickly take care of the vector diagrams. The primary force diagram. So, it will be 1 and magnitude is m reciprocating omega square r, this will be number 1. Number 2 will be just opposite in this direction, number 3 will be of same magnitude in this direction, and number 4 will be in this direction. And the whole thing, as you know, is rotating with a speed omega. So, it is very clear that the force diagram produced by the centrifugal forces of hypothetical masses placed at the crank pins, they balance themselves. If that balance themselves, those balance themselves, then obviously their components in any direction will be also balanced. So, the primary forces are balanced. Now, primary moment. Primary moment, we can draw the diagram. So, for number 1, it is in this direction. So, since this is the cylinder's engine center line and this is the point about which we should take the moment. So, this will produce a moment in the right hand direction whose magnitude is known, this into 1.5 a. Then this one is in the downward direction. So, it produces in this direction and magnitude is this into 0.5 a. Then this one is in this direction. So, it produces again a force, a moment in this direction whose magnitude is again this into 0.5 a. And then finally, 4 produces a moment in this direction by right hand screw rule and comes here. So, the resultant moment and the whole thing of course, is rotating. So, primary moment is unbalanced, very clear, and at any instant, since the forces are vertical, so moment will be in the horizontal direction. So, or in a direction perpendicular to the board. So, this will be the direction of the actual balance. So, component you have to take. So, at this instant of course, we are getting the full one and the magnitude is simply this plus 0.5. So, 2 m reciprocating omega square r a, that is the magnitude of the unbalanced primary moment, the maximum value. What about the secondary? Now, when you draw the secondary crank, now 2 into 0, that is for cylinder number 1 or crank number 1, it will be 0. Then 2, it is at an angle 180 degrees or pi. So, 2 of that will be 180 degrees. So, it will be like this. Then 3 is also again 0. So, 2 of 0, 2 into 0 will be again 0, and 4 is again 180 degrees, 2 of that will be again 2 pi. So, now you find secondary cranks are all aligned and they are rotating at a speed 2 omega. So, the forces will be this is by the first cylinder which will be lambda by 4 m reciprocating 2 omega square r for the second cylinder in this direction, third cylinder in this direction, fourth cylinder in this direction. So, primary forces or secondary forces are unbalanced. Now, secondary moments you will find will be balanced, because this will produce a moment in this direction, then this will produce again a moment in this direction, then this will produce again a moment in the opposite direction, and this cylinder 4 will produce a moment in this, and the whole thing is rotating, both these also is rotating, and here we started here. So, you have come back, so therefore, resultant is 0. So, secondary moments are balanced. The important thing now we should note that in this kind of situation where we have taken a 4-stroke cycle 4-cylinder engine with a firing order 1, 2, 3, 4, the primary forces are balanced, primary moments are unbalanced. We should try to balance the primary as much as possible, because the magnitude is maximum. Secondary forces are unbalanced, but secondary moments are balanced. Now, you will see what actually we want to tell now, which is very important, that just by changing the firing order, it is possible to improve the balancing situation. Suppose the same engine, we take the firing order as 1, 2, 4, 3. That means first cylinder fires, then second cylinder fires, then fourth cylinder fires, and finally third cylinder fires. So, this will be the isometric view of the common crankshaft 1, 2, 3, 4, and crank diagram will be what? Primary crank, one, 2, 3 and 4, and the whole thing is rotating. And secondary crank, 1 will be here itself, 2 will be also here, 3 will be also here, 4 will be also here, and the whole thing is rotating at 2 omega. This is the secondary crank. The interesting thing will be now if we draw the force and moment diagrams. So, primary force diagram, if we want to draw here, so obviously primary force is you can see 1, then 2, then 4, 3. So, 1, 2, 4, 3. So, primary force balanced. Earlier also it was balanced. Primary moment. So, primary moment, the force 1 will produce moment in this direction, and that is m reciprocating omega square r into 1.5 A. Second one is in this direction. So, that produces a force in this moment in this direction, which is 1/3 of this. Then 3 is again in downward direction. So, it will produce a moment in the direction opposite to that and same magnitude. And finally, the fourth one, which is in the upward direction, that will produce a moment in this direction, and the whole thing is rotating, this primary moment diagram. And as you have seen that where we started, we have come back there. So, therefore, it is balanced. So, we started here and come back here. So, therefore, it is balanced. So, this is the difference that we are earlier our primary moment was unbalanced. Now, we have got the primary moment balanced just by changing the firing order from 1 2 3 4 to 1 2 4 3 and the crankshaft arrangement being this. The secondary, if you can find out, you will find, since secondary crank is like this, indistinguishable from the secondary crank of the previous one. So, you will find that the forces will be obviously unbalanced, and moment you can check what it is. So, we will find it will be first cylinder will produce in this direction, second cylinder also produce same force, third also same, and fourth also same. So, unbalanced. Secondary moment, secondary moment you will find first one is producing in this direction, second one is also producing in the same direction, third one is producing again in the same direction, third one is down like second. So, it will produce something and fourth one is at the end. So, it will also produce the same. So, here again you find that secondary moments are balanced. So, overall there is an improvement, because earlier the secondary forces were unbalanced and primary moment was unbalanced. Just by changing the firing order, we have achieved total primary balance and only the secondary force unbalance. So, now I think this sends the message that firing order is very important, and one can take up the case of 6 cylinder engines with 4 stroke cycle, and the crank arrangements, if you take one takes, then it will be found that wherever it is symmetric about the midpoint, like say if I take a 6 cylinder engine 4 stroke cycle, so if I keep a firing order like 1, 2, 3, 4, 5, 6, it is rotating like this. So, first this fires because it is at the top, next comes 2, next comes 3, next comes 4, next so on. So, after every 120 degrees rotation one firing takes place, and total 300 I think 720 degrees will be taken, that means 4 pi, to make all the cylinders fire once. Now, with this, if you keep on doing the same kind of analysis, you will find primary forces will be balanced, secondary forces will be balanced. Now, one should be very careful in drawing the primary and secondary cranks. So, if this is the primary crank, say 1, 2, 3, 4, 5, 6, this is the primary crank. Secondary crank, 1 will be same, because 0 into 0 is, or 2 is 0, 2 the angle is 240 degrees. So, double of that is 480, that means 360 plus 120. So, 2 will be here, then 3 is 120, double of that is 240. So, it will go, it is in the direction of rotation. 3 will be here, 4 will be again here, then 5 will be here and 6 will be here. So, this will be the secondary crank. So, you can see that if we place masses at the crank pins, the primary forces will all balance because they are symmetrically placed. Secondary forces will be all balanced as they are also symmetrically placed, but primary moments and secondary moments may not be balanced. To achieve both primary and secondary force balance, to achieve primary and secondary moment balance, complete balance up to secondary, we have to take crankshafts which are symmetrical like this. Either this or so it is 1, 2, 3, 4, 5, 6. So, firing order in this case will be 1, 2, 3. After 3, of course, 6 will be fired, then 5 will be fired, then 4 will be fired, then again 1 will fire. In this case, it will be firing order will be 1, then 3, then it may be 2, then it may be 6, then it may be 4 and 5. Like that, whatever we distribute, the arrangement of the cranks in the crankshaft should be symmetric about the center line, engine center line. You can see this is symmetric about this, this is symmetric about this. So, in all these cases, if we draw the primary force and secondary force, primary moment, secondary moment, it can be easily shown that it will be completely balanced up to the secondary. Thus, the arrangement of the same engine, if properly designed, can be completely balanced without taking the trouble of attaching active measures like putting separate balancing masses. The unbalanced forces themselves will neutralize with each other. So, in the next session what we will do, we will take up some other kinds of arrangements of the various cylinders or engine or slider kind mechanisms, so that we get also proper running without balancing, and two such cases are popular. One is V engine, another one is radial engine. In the next session, we will take up those two.